So we're looking now at the problem of a film falling and a gas dissolving into that film. And whenever we talk about a falling film, that's against some physical surface. So for instance, there's a wall here, and we might have a gas out here, and due to condensation or some such process, or simply through the introduction of a liquid against that wall, we will form eventually a film that falls down that wall. Right, so when I say falls down the wall, I really mean due to gravity, the liquid that's built up here is basically going to creep down this wall, and as it does so, the gas that's out here, or components from that gas, are in principle free to diffuse into that film. And you might choose to do this for simple cases like adsorption. So if we have walls with enough surface area, and you might think about creating a system with many plates, for instance. So if we create a plate or a row of plates here, and we wet all these plates with some liquid, then expose all those plates to a gas, then we can start absorbing from the gas onto those plates, right? Simply through adsorption into the film that's sitting on those plates. So we have some liquid film that's falling down this wall, and as it's falling, we have the gas components diffusing in here. So in effect, the surface of this film is the surface area for transfer between the gas and the liquid. All right, so that's in principle the physical situation. Let's now define for ourselves the dimensions of the system. I'm just going to redraw the wall right here, and here's the film. And of course we can imagine that this wall will extend to some distance there, and of course the film is falling in the same way throughout. So we are really interested in what's going on here. Right? If you look in this direction, you've got the same kind of film. So the film is falling in the same way if we look in this direction. So let's define Z to be the distance down the wall. And then let's define X to be the distance from the surface of the film into the film. And we can also define Y to be the distance along the wall. And just be careful, these arrows are of course in different directions. You've got X is the thickness into the film. So here now I'm shading this way for the film itself. Of course the wall is here. And so looking into the film, X counts from the surface of the film into the film until eventually we meet the wall, whereas Y is looking along the film, and then Z is the direction down here. And we are also provided with the velocity relationship. We are told that the velocity in the Z direction is a function in X, and that function looks like this. There's some parameter u max, so there does exist some maximum velocity, which is 1 minus x over delta squared. Right, and if you think about the dimensions here, you've got at x equals delta, right? Remember, x is from the surface of the film looking in towards the wall, and delta is the thickness of the film. So let's say the thickness here is delta. When x equals delta, we are in effect going from 0 all the way to the wall here, right? The film thickness is delta, so from 0 taking delta that way, we meet the wall. So when x equals delta, this becomes a 1, and so it's 1 minus 1, and so we'll have a 0. So we have 0 velocity here, and then when x equals 0, then we are in effect looking on the surface of the form. When x equals 0, this becomes a 1. This whole factor becomes a 1, leaving us with u max. In other words, u is 0 here and u max here. And that's what we expect, right? We expect 0 slip on the wall, and we expect the maximum velocity out here where there's no viscous drag, or there's less viscous drag. Of course, you have viscous drag from this side of the fluid, but on this side we are exposed to the gas. So this is the fastest moving, if you like, the fastest moving part of the form. So we get u max here and the 0 velocity there. So those are the dimensions x, y, and z. So now we want to develop the material balance. So using these definitions for our dimensions and this velocity distribution, please develop the material balance. So do this now. It should take about 10 minutes. And let's pause the video while you go ahead and do that. Okay, so to develop that mass balance, I'm going to take some control volume inside the form. So let's imagine a little box in the form here. And of course, that needs to be in 3 dimensions. So I'm just going to draw that box out separately here. So I'm going to redraw that box. So we have our little box. And of course our form is here and our wall is here. And we have defined, we've got x in this direction, we've got y in that direction, and we've got z in that direction. So if you think of this box, we can have flux in principle in all directions. First off, we can recognize that in the y direction, there's no real difference, right? If you consider the y direction here in the broader picture, you've got in effect the same thing happening at all y positions. You've got a gas out here and diffusion into this form. There's no difference in the y direction. There's no change in the y direction. If you think about the z direction, of course there's a difference. There's the form building up, and you've got velocity. You've got the fluid flowing in effect in the z direction, so there is going to be a change there. And in fact, the main point is, as this form flows down this wall, it's going to accumulate the gas phase component. So component A, let's just call it out in the gas phase, is going to diffuse in at all points down this film. And so as the film falls, it's going to pick up more and more of component A. So there is going to be a change in concentration in the z direction. And similarly, if we look in the x direction, you can imagine that out here you'll have a relatively high concentration of component A, because the gas is out here, is closest here. And then as we look further into the form, you have a lower concentration. So we anticipate there may exist a concentration that looks something like that, a concentration profile in the x direction. So there are changes in the x direction and changes in the z direction, but no changes in the y direction. So we won't consider the y direction. And having said that, let's write a balance on this little box. So let's define for ourselves the total number of moles there. Of course, we can take the concentration. We can define the concentration at some position x, y, z. And so we will define our box to be at position x to x plus delta x. And then z will be, z starts up here, z to z plus delta z. It's a bit of a squeeze. And then here it's going to be y to y plus delta y. So we can say that in terms of the total number of moles in this little box, we can estimate that by multiplying the concentration by the volume of that box. So the volume of the box is, of course, delta x, delta y, delta z. And then we want to know the rate of change of the number of moles in that box. So ddt of all this, and that's going to equal it's going to equal changes in the x direction, right? We did say we would have a concentration difference in the x direction. So we can say there will be some molar flux of component A at position x. And so we can see at x, that's the flux into the box. And of course, this is the rate of change of moles. This is molar flux, so we need to multiply by the area. And if you look at the area that's normal to the flux in the x direction, it's this area, and we can see that that area is going to be delta delta y multiplied by delta z. So that's Na at x delta y delta z. And then the flux out of the hidden face there, so on the other side in the x direction, there is also a flux that's leaving that box. So we can write that as minus Na at x plus delta x, and then that's delta y delta z. So that's flux in the x direction. Then, of course, we may also have flux in the z direction. So looking at this top face and this bottom face here, we'll have coming into the box from the top down, we'll have a molar flux at z, and that's in the z direction. I should have said this is the molar flux in the x direction here. So the molar flux in the z direction at position z multiplied by the area. And if you look at this upper area here, you can see that looking in this direction, it's going to be a delta y, and then in this direction, that's a delta x. So that area is delta x, delta y. Delta x, delta y. And then, of course, that's a plus, that's a flux into the box. And then we lose component A due to molar flux down out of the box here. So that will be minus flux in the z direction at position z plus delta z, then times delta x, delta y. Okay, so that's the balance so far. And of course, we can do the usual thing. We can divide through by delta x, delta y, delta z. So those will cancel, leaving us with ddt Ca is, and then here we've cancelled delta y, delta z. We still have to divide by delta x. So it's Na at x minus Na in the x direction at x plus delta x, and then that's divided by delta x. And then similarly, this one is going to be plus Na z at z minus Na z at z plus delta z divided by delta z. And so, of course, if we take the limit for delta x and delta z going to 0, we're going to get ddt Ca is di Na di x plus di Na di z, right? Where, of course, the di Na di y is not considered to be significant. There's no change in that direction, right, along the form. So that's our material balance. It's still not in a specific enough form. So we have to think about this. We have to think about Na. So Na in general, in let's say the ith direction, is going to equal the diffusion flux. So that's going to be minus dAB di CA di I plus UCA. So convection flux and diffusion flux, that's generally what we have. And then if we look here at these two possible fluxes, in the Z direction, clearly the majority of the flux is due to the film falling. So simply because this liquid is falling and carrying down with it component A, the major flux contribution is convection. So of course we may have diffusion in this direction also, but we would normally consider that small in comparison with the actual falling of the film. So we can simplify in the Z direction that this flux is largely this term. And I should say here velocity in the I direction. Now, if you look in the X direction, we don't really think of there being convection in this direction. You could argue that, well, a film is kind of a free surface, and there is some kind of rotation here because you've got a zero velocity here, you've got no slip on the wall, so there's some kind of rotation. But in principle, we don't really think of there being flow in the X direction. This is a falling film. There isn't really flow in the X direction. It's all in the Z direction. So we would normally just neglect convection in the X direction and say that any flux is largely due to diffusion. So there's diffusion in this direction, but not really flux, convective flux. And so if that's true, then we can simplify this. We can say, okay, this first term in terms of the X direction is really about diffusion. So this becomes minus dAB di CA di X. And then in the Z direction, diffusion is considered small in comparison with convection. And we would write this as plus UZ CA, where of course UZ is given to us as this expression. So we can substitute this here. Right, so this is of course flux, so I shouldn't write it like this. I should say, so this is the molar flux in the X direction. So I need to write this as ddx. So let me just erase here a little bit. So this is to be minus ddx of diffusivity, and this is ddz of convection. So we can write overall then that dCA dt is here dAB is a constant. So if we imagine in the X direction the temperature is approximately constant, then the diffusivity will be the same at all those X positions. So we can take that out as a constant of differentiation. So this is di 2 CA di X squared. And then in the Z direction, we have an explicit form for UZ, and the concentration itself, that's generally also changing. However, if you look at UZ, right, let's go to this form here, you can see that UZ itself is not a function of Z, right? UZ varies with X. It doesn't really vary in Z. So that's because if you think of the velocity profile through this film, so let's draw it out here. Here's the wall, and then here's the film. And so let's take some position Z. So at some position Z, if we imagine our velocity profile, it's going to be 0 here, and then it's going to do this sort of thing. So it's going to be fast here, right? U max, you are quite fast near the surface of the film, and then it starts dropping due to viscous drag, because on the other side of the film, it's not really flowing, right? No slip at the wall. So due to viscous drag between a definitely flowing part and a not flowing part, there are these in-between values, right? Viscous drag causes this value to change continuously, right? So we have a velocity profile like this, and according to the information given in the problem, this is not a function in z. So if that's the case, when we differentiate this, as much as this is velocity in the z direction, it's a constant with respect to z itself, because it's not a function of z. So we can just write this as plus uz, which is of course u max 1 minus x over delta squared times ddz of Ca. Okay, and so that's our mass balance generally. Now we can anticipate that a steady state will develop, right? If your film was falling for a long time, eventually we will achieve some steady concentration of A at all positions through this film. So we will reach some steady state eventually. So at steady state, we can rewrite this. At steady state, of course, that's a 0. And so we can restate this as u max 1 minus x over delta squared ddz Ca equals dab di 2 Ca di z squared. Right, and that's the mass balance that we are looking for. Okay, so on to the next part of the problem. We now want to determine the governing boundary conditions for this problem. So this should take you about 2 or 3 minutes to come up with. So do this now. Let's pause the video while you go ahead and do that. Okay, so continuing with this problem of developing the mass balance and the boundary conditions, we've derived this expression. And of course, this applies to interior points in the fluid. So if we look inside the film, then we can define what's happening there. And now we have to think about what happens on the boundaries of that film as well, if we want to solve this equation. So first off, we can say that if we think about right at the top of that film, so for instance, if we have a plate like this and the film is developing on the plate. So what we said earlier was that as the gas phase component starts diffusing in, it accumulates and the concentration will go up as we go down the film. But of course, right at this uppermost position where the film has first started to develop, we haven't had any time for A to accumulate there, right? When we look further down, of course, there's a higher concentration of A. But right up top, A hasn't as yet had any time to diffuse into that film, and so we can treat the concentration there as a 0. So that's the first useful boundary condition for us. We can say that the concentration of component A, which does vary in both x and z, so for all x positions, looking at specifically the top where z equals 0, that should be a 0. So that's the first boundary condition that we can specify. Then for the second one, we can think about what's happening out here on the film side. So on the film side, on the surface of the film, you have the gas out here, and then you have the liquid in here. So there will exist some surface concentration of component A in this film, and that surface concentration may be determined in a couple of different ways. Number one, if there's no external mass transfer resistance, and remember, in principle, there may be, right? There might be a concentration difference between the surface on the gas and the bulk gas out here. So there's, if you like, there's a bulk gas out here, and then near the film, we are diffusing from the bulk into the film, right? So there, in principle, exists some concentration gradient. And so if we have the mass transfer coefficient out here and so on, we can estimate the difference between this bulk concentration and that surface concentration. So we can eventually determine a surface concentration here. That's one. And then that applies only on the gas side, remember. We still need some equilibrium difference between the gas and the liquid, right? Remember, when we are writing the boundary conditions, we are writing that over this particular phase. So we've written a balance on the liquid film. So talking about the gas out here doesn't complete the picture. We need the boundary condition in the film. So even if we happen to know this value here, we still need to translate that into a liquid concentration value. So let's say that we do happen to have the gas phase value here. So let's write this as Ca in the gas on the surface, or rather the gas immediately next to the surface of the film. So if it's defined like that, then we might have some equilibrium relationship. So if we have the gas liquid equilibrium constant of component A, right, so let's say that equilibrium constant is simply K, then we might be able to say something like Ca gas surface times K. That will give us Ca in the liquid on the surface. Sorry about that. So we've got here in the gas phase, we've got the concentration near the surface, and then we use the equilibrium constant to translate that into the liquid phase surface concentration, and we're just going to call that CAS. So we can then identify that as a second boundary condition. So we can say the concentration of A near the surface, in other words, where x equals 0. Remember, we defined x from the surface looking into the film. For all z positions, that's equal to CAS. Right, so there might be a little bit of work behind trying to find this value, but in principle we can do it. We can look up equilibrium constants, and we can work out mass transfer coefficients, and we can translate a bulk gas concentration into a surface concentration, and then through the equilibrium estimate the concentration in the liquid right next to that gas. So we can somehow get a number like that. It's not that difficult. Right, so once we have that number, then that boundary condition is fully specified. Then for the third boundary condition, we can look inside this film and imagine what happens right here. Right, so we've so far got what's happening at the top up here. We've also got what's happening on the surface of the film. And then if we look right through the film near the wall there, we can imagine that, well, if this wall is not allowing component A to diffuse through it, right? If this wall is impermeable to component A's diffusion, then A might accumulate near the wall until it reaches some value, and then it's not going to diffuse in anymore. So it's going to look like this, right? Your component A concentration here will be such that there's no flux, there's no diffusion flux into the wall. So if there's no diffusion flux into the wall, then there's no driving force for diffusion, and so the gradient there must be a 0. So we can say here that at position x equals delta, the gradient must be 0. So ddx Ca at x equals delta for all positions z, that must be 0. Right, so no flux into the wall. That's what that condition means. So that's that is a complete set of boundary conditions for this equation, and we can solve it numerically. So yes, we can discretize these equations, and I won't go through that. You've seen that plenty of times now, how to discretize equations like this. And you have boundary conditions. So you can definitely solve this, and maybe we can just anticipate what it would look like. So if we were to plot with, let's take x in this direction and z like that. So we can imagine, of course, at the top of the wall where where z equals 0, we said that's going to be a 0. Then as we look further down the wall, we've got more of component A making an appearance. So and we want to be careful. The surface is here, and the wall is here. So we're going to start to see some of component A appearing here. Then as we look further down the film, more of A is going to penetrate, and so A is going to start appearing in our system like this. Looking at this at z equals 0, and at z is when x equals 0, there is let's see, there's a correction we have to make. We are stating here that at x equals 0 there's a surface value, so I need to correct this a little bit. Here all these values are going to be fixed, so these are empty points. Let's think of them as empty points. And there exists some surface concentration CAS. So even this is an empty point. So there is a single value, a surface concentration, and then initially, the moment we look away from that from the surface of the film, there's a 0. And then similarly here, if we look some distance down, right? So of course here we are looking further down the tube. So Z is increasing in this direction. So if we look some small distance further down the film, we will have some of A starting to penetrate the film, and it won't have penetrated all the way to the wall as yet, excepting at the 0 position. So at x equals 0, it's fixed at that surface concentration. So because of equilibrium between the gas here and the liquid there will always exist some surface concentration, and that's in the liquid. So right, if you imagine right on the inside of this film, there is some concentration which is a discontinuous value. So there's a value here, and then there's a different value immediately next to that. So it is a discontinuity. We are always fixed to this concentration CAS for x equals 0. And then the moment we start looking inside the film, there's a continuous drop as we look into the wall. And it drops in such a way that we always have a 0 gradient here. Right, and if we look far enough down the wall, then we'll get something eventually like that. So let's just draw that properly. So we can anticipate our solution will look something like this. Okay, so if you solve it numerically, that's what you'll get. A solution to this set of equations does also exist. And if you look that up and you apply it here, you should see the same kind of thing. Okay, so a solution to this equation with these boundary conditions does exist, but we also want to think about whether we can't approximate this situation such that one of the earlier PDEs applies. So if you have a look at tutorial 2, there was a different situation, right? We had an equation that looked similar. We had a ddt of Ca. It was basically the diffusion equation, right? Unsteady state in concentration. This one is steady state, but we had a t instead of a z, and we had a d2ca dx squared or something like that. So we had a very similar equation. We had different boundary conditions. So I'd like you now to revisit that problem and think about, is there any way that we could find a similarity between that system of equations and this one? And is there any way for us to physically justify that this system can approximately behave like that system? So please go back, have a look at tutorial 2, and try to propose a change to these boundary conditions such that we can also use that solution instead. Do this now. It shouldn't take more than 10 minutes. So I'll pause the video while you go ahead and do that. Alright, so looking back at our tutorial 2, you might recall this problem where we had diffusion into this into some drug substrate. So we had some component diffusing into that drug substrate, and this was the differential equation that applied. And so we had diffusion of component A into the drug substrate over time and over the thickness of the substrate. So we have here at T0 an initial condition applied. At Z0 we have a surface concentration, and then if you look far enough into the substrate, you will get the initial value of the component A there. So that was the system of equations we had for that case, and the advantage being that we can then apply this nice analytical solution. And in our problem right now, we have a different situation, right? We have this differential form for our boundary condition, which is not the same as this one. This is about the same, right? If you change the variables, if you accept for z instead of z, if you use the variable t, then you can define constants here. Of course, out here also, this is also different. So that's another part that we have to think about. So in the governing equation, there is a non-constant coefficient as well. So we need to do some work there. And then the other piece of work is here. This is different. These are largely the same because there's a constant. Fine, that's a special constant, a 0. But it's a constant nonetheless. And then, of course, that's a constant. And then those two constants are occurring at z equals 0 or t equals 0 in the other problem, and then x equals 0 or z equals 0 in the other problem. So that's what we have here. But basically we can see generally we can convert the one problem to the other in terms of these two only. Then let's first deal with this part. So if we think about this form, if we imagine the form to be thick enough, so let's take the wall here, and if we imagine that this form is thick enough, or another way to look at it is if this wall is long enough, and if we look far enough down the wall, then we can imagine that the film will eventually be thick enough that the diffusion of A into the film is not as fast as the convection, the falling of that film. So in that case, this thickness is in effect infinitely large in comparison with the free space scale of diffusion here. So in that situation, we can say that, well, this velocity is going to be approximately constant. And well, I shouldn't say constant, I mean uniform. And of course we know there's a zero velocity here and then some maximum velocity here, and the viscous drag is going to give us that change in velocity. But if this film is thick enough, then that zero velocity region isn't going to last for very long. So we are definitely going to get a zero velocity, but it might level out if we look far enough down the tube, that we can treat this entire velocity as in effect on average close to u max. So we can replace that whole velocity field by just the u max value, and so that's how we can translate the governing equation itself. So we make the approximation that our system of equations becomes simply u max di Ca di z equals dAb di 2Ca di z squared, or in our case it's di x squared. And of course here you have a before we didn't have a constant here, but you can just divide through by this constant, right? So you would say divide by u max here, and then the general solution doesn't care whether you've divided by u max here. It's just treats that as some constant, right? In our solution we would just have dAb over u max down here. So that's the first simplification, or the first approximation we need to make to find equivalence between those problems. And then the second one is, as we said, in the boundary condition, in terms of what's going on at the wall. So again, we said that this film might be considered thick enough that looking at just at the wall, we can take this value as being far enough away from the surface that diffusion hasn't really reached there, that this film is falling fast enough that component A doesn't really have time to reach there. In other words, we take that the concentration of A at x equals delta in Z is going to be Ca Ca naught, or actually 0. There's none of A at the wall. Right, so that becomes, if you like, 3 dashed. Right, the first two are the same. So Ca at x for Z equals 0 equals 0. And when x equals 0 for all Z, we have CAS. So if you look at this system of equations now, it's identical to this problem for which this solution applies. And so this approximation has been made by several researchers and applied, and it has been found that this solution does approximate what goes on in the form fairly well. So it is a fairly good approximation that works. So that's how you can translate the one problem into the other. But like I say, there's no real reason to do that, given that even for this problem, there does exist an analytical solution, and you can also use the you can also just solve it numerically. So today it's less of a concern. Several decades ago, when computational resource wasn't as available as today, and also when solutions weren't as available, right? It perhaps took a long time to find a solution to this equation, whereas this set of equations was solved by then. That might be why we see so many notes on this approximation. But anyway, it's interesting, and it gives you some of the useful flavor of engineering, which is in making good approximations to take advantage of existing solutions. Okay, so that's